All right, can you guys hear me? Okay. Okay, so Tatiana, looks like you have questions for about the homework. Yes, we have to go over that during the office hours because we're falling behind the the lecture. So yeah, send me a screenshot of the homework question that you're having trouble with, and we can schedule an office hour. Okay.
Great. Thank you.
Okay. Give me 1 second.
Dr. Lee, will your slides be available on Canvas after this lecture?
So today we're going to finish chapter 14. So if we finish, I will upload that on Web Campus.
Okay,
Hopefully we can, yeah, hopefully we can finish it. Okay, we have 100 students enrolled in this course, but we only have 56 students so far. So, but I don't want to wait too long. So I'm just going to start the lecture. All right. So, so far we have explored intensive details about the rate law. Okay? The ultimate purpose of studying the rate law is, or study all those first order, second order, zero order rate equations, is to explain a reaction mechanism. Okay? A reaction mechanism is a step by which chemical reaction occurs where reactants become products. This is called chemical equation, and this is reaction mechanism. Okay, so the rate law is going to explain the reaction mechanism. So chemical reactions can occur through a single step or through several different steps. So if it's occurring through several different steps, it's called multi-step. Okay, so if it's A going to B, if B is a desired product, this is a single step reaction. If you're going from A to B and B to C, if your C is the desired product, the journey of going from A to C, you need multi-stepped reaction. Okay, so any reaction that occur in a single step, this is called elementary reactions. Okay, if chemical reaction involves several elementary reactions, this is called multi-step reactions. So this is one elementary reaction, this is one elementary reaction. Okay, so multi-step reaction composed of several different elementary reactions. And these are all showing an elementary reactions where only a single reaction step is required for a product to form. Okay, so these are all elementary reaction, one step reaction. Okay, the term molecularity Molecularity basically explains how many molecules are involved in a step of an elementary reactions. Okay, when a single molecule of reactant becomes product, we say this is a unimolecular elementary process. Okay, when the reaction is first order, it is unimolecular process or unimolecular reaction. When two molecules of reactants become product, we say this is bimolecular reactions or bimolecular elementary process. So when reactions are in second order, the reaction is bimolecular. When you have three molecules of reactants becoming product, we say this is termolecular elementary process. Okay, when reaction is in third order, the reaction is termolecular. So I know you guys are familiar with the first order reaction, second order reaction, because we've explored these two reactions thoroughly in the previous slides, which are unimolecular, bimolecular reactions. But what about termolecular? The termolecular reaction that we have just seen in the previous slide is very rare to observe. Okay, this is very rare. Okay? This is because all three molecules, if you have three reactants, all three molecules have to collide simultaneously with appropriate orientation and energy. And in order for all these three aspects to meet at once is extremely challenging. And that's why thermomolecular reactions are very, very rare to observe. Okay, so thermomolecular reactions are much slower than or unimolecular or bimolecular steps, and nearly all mechanisms that we will use is going to be unimolecular or bimolecular reactions. Okay. So elementary reaction is a single step reaction where reactants become product directly. Okay. However, most reactions occur through multi-step reactions. Okay. Which means two or more elementary steps are involved. Okay. Most reactions are like that. So for example, reactant A plus reactant B produces C. C plus D equals E. If E is your desired final product, if the final product we want to achieve is E, then the product E is obtained through two elementary reactions. I already explained this in previous slides. So for these multi-step reactions, each elementary steps has its own rate constant and activation energy. Each individual elementary steps will have each their own rate constant and activation energy. Okay, the slowest elementary step often limits the overall reaction rate, and that elementary step which is slower, that is called rate determining step. Okay, so let's take a look at the diagram. If you look at the diagram, the picture in toll A is slowing down the vehicle. So the arrival time at the destination is going to be affected by toll plaza A. So the toll plaza A is going to be the rate determining step for this entire trip. Let's say if toll toll B is slowing down the vehicle. Okay, so then the arrival time to the destination is affected by toll B, and we say toll B is a rate determining step for this trip. Okay, so if this is step one, if this is step one and if this is step two, if step one, if this elementary reaction is a slower reaction, if it's occurring slowly, then this step one is going to be the rate determining step. Okay, it will affect the it will limit the overall reaction rate. Okay. So when it is a multi-step reaction, the overall rate, this is what I've just said. When it is a multi-step reaction, the overall rate law for a reaction is affected by the step with the slowest reaction rate, or in other words, the overall rate law for a reaction is governed by the rate determining step. Okay, so keep that in mind. And for a plausible reaction mechanisms, below criterion have to meet. Okay, those are: number one, the stoichiometry must be obtained when all steps are added up. Each step must balance like any equation. All intermediates have to be made and used up. All catalyst is used and regenerated after the reaction. And let's take a look at an example about this criterion that we just discussed. Okay. So let's take a look at a specific example of what a plausible mechanism looks like. Okay, the overall equation for nitrogen dioxide, carbon monoxide generates nitrogen monoxide and carbon dioxide. Okay, and it is found experimentally that the overall rate law for this reaction is second order in nitrogen dioxide and zero order in carbon monoxide, because carbon monoxide does not take place in the overall rate law of this reaction. We also found experimentally that we also experimentally know that the reaction rate is slower for the first step, for the initial step. And these are the only given information, and while we don't know specific detailed steps about the equation, we can propose a mechanism that meets the experimentally found rate law, and later we check and see if the proposed mechanism is plausible mechanism or not. So this is a journey to find a plausible mechanism for step one, step two, when we don't know exact step one and step two reaction mechanism. Okay. So since we know that the first step is a rate determining step, the first step will give the rate law for the overall equation. Okay, the overall rate law equation is here, provided here. So the step one equation has to be NO2 plus NO2, because this will give rate law of this. Okay, and this reaction, the nitrogen dioxide is known to generate nitrogen oxide and nitrogen trioxide or nitrate. Okay, however, since we do not see the nitrogen trioxide in the stoichiometry, this is an intermediate which needs to be used in a faster next step too. Okay, so if we incorporate the intermediate.
Dr. Lee?
Yes.
I'm just trying to see if I'm getting this. So the first thing we have to do is find the slowest step in the mechanism, because that's
that information is already provided.
That information is provided.
Yeah, these three are provided information, and you want to find the multi-stepped reaction mechanism.
The reaction mechanism, that's what's going to tell us the slow initial step, right?
No, slow initial step is already experimentally found. That information is already provided. So these three are the provided information. You are provided the overall equation. You are provided the rate law for the entire reaction, overall reaction. And then you know that the initial step, step one, is the slower reaction. Okay, so they want you to propose a mechanism for step one. They want you to propose a mechanism for step two. Okay. They want you to propose a plausible. Do you see that we learned about the criterion that a plausible mechanism requires? So they want you to propose a plausible mechanism for step one and step two. See if that meets the overall reaction rate law they experimentally found or not. Okay.
Thank you so much for the clarification.
Yeah. Sorry if I was going too fast.
It's okay.
Okay. So, yeah. So since we do not see this intermediate in the overall stoichiometry, if we incorporate this intermediate along with the carbon monoxide that we did not utilize in the step one, the fast step two, this is slow step, this is fast step. The fast step two reaction mechanism would be NO3 something like this. Again, we're just proposing a plausible mechanism according to the provided information. These are the proposed. Okay, proposed mechanism. Okay, so these are the step one and step two that we have proposed. We want to check and see if this step one and step two mechanism that we propose meets the plausible mechanism criterion or not. Okay, the criterions are: the stoichiometry must be obtained when all steps are added up. Each step must balance. Intermediate should be made up and used up. We didn't use any catalyst. Okay, so let's see if the stoichiometry is obtained when all steps are added up. Okay, so if you add up all the, when you add all the reactants and when you add all the products, this is what you're going to have. These are the step one reactants. These are the step two reactants. Product side, you have okay. So then intermediate cancels because it appears on both sides. Cancels. Okay. Oh, wait.
Dr. Lee, did you mean to put CO instead of
sorry.
NO when you had the second step?
My mistake. NO2 and CO2. NO2, NO3, CO. Does that look right? Okay. All right, so then intermediate cancels. These cancels. And you're left with NO2 plus CO.
Dr. Lee,
Yeah.
I hate to slow you down. I really apologize, but how did you come
Oh.
up with the proposed mechanisms
Proposed mechanism?
for step
For-
one and step, yeah,
Okay. So for step one, I came up with this because we know that we know that the initial step, it's already provided information that first step is the slower step. That's already provided information. Okay. So we know that, as I mentioned before, the slow step will govern the overall reaction rate, right? Do you agree with that?
yes,
Yes. So we know that this rate law that they provided is from the slower reaction, which is step number one, correct?
yes, I'm starting to see it now.
Yeah, okay. So
Okay.
that's why in order to have this kind of this rate law, this is what I can come up with. It can be something else, but this is what I'm proposing. Do you understand?
Yes, I see how the
Yeah.
reactants, how you got, but where did the NO3 come from?
Oh, this is just a reaction. So if you do a nitrogen dioxide plus nitrogen dioxide, this is what you will get. Okay? It's
Okay.
just like if you add hydrogen, if you add oxygen, you will get water. It's just a known mechanism.
Okay.
Yeah. So this is what I'm proposing. Okay? Again, I'm emphasizing the word proposing. Okay? Later on, we will see an example where a different reaction mechanism also meets this rate law. Okay? So this is a proposed mechanism. It does not always necessarily have to be this reaction mechanisms to meet this rate law. Okay? I'm proposing. Okay? Did that clarify?
Yes, thank you so much.
Okay. All right. So I added the product side and the reactant side and product side, and I see that the resulting equation agree with the overall equation up here. Okay. So the first criterion is met. The stoichiometry must be obtained when all steps are added up. When I added all the steps up, when I add step one and step two, this is what I got, and this met the overall equation. Okay, so that's why I know that step one and step two mechanisms that I proposed, it seems right so far. Okay, let's check another criterion. It says each step must balance like an equation. Each step is balanced, right? All the steps are balanced. So this is checked off. All intermediates are made and used up. The intermediate NO3 made was used up. So checked. So because this proposed my mechanism that I proposed meets all the criterion for a plausible mechanism, we can say that these two mechanisms that I proposed make sense, and these are the plausible mechanisms that agrees with the experimentally provided information. Okay, so this is a proposed mechanism. I'm sorry. These are the proposed mechanism. And we have found that this proposed mechanism agrees with the experimentally found information. Okay. All right. So let's take a deeper look at the intermediates. In the previous example, the NO3 that was made up and used up within the reaction, that was an intermediate. An intermediate is not a reactant, or it's not a product. It is also not the transition state. Okay, transition state is a state where the organizations of the atoms at its highest energy state. And transition state is a state of transitioning where reactants are transitioning into products, normally where two reactants are positioned nearby to form new bond and form product. But intermediates are lower in energy, and intermediate is what you actually generate to form from the first step of the reaction, okay? And sometimes you can actually isolate and identify an intermediate, okay? So keep in mind that intermediate is different from the transition state, okay? And intermediate has to be made up within the reaction and used up within the reaction. Let me write that down. Within a reaction, okay? All right. So let's take a look at, let's solve a practice exercise together. The decomposition of nitrous oxide is believed to occur by a two-step mechanism, and the information is already provided that the first step is slower step, second step is fast step. So we immediately know that the slow step will govern the overall reaction rate. This step will give us the rate law, okay? So the question A is asking to write the equation for the overall reaction, B, write the rate law for the overall reaction. So in order to write the equation for overall reaction, you write all the product reactants out, you write all the you add all the products and see what you get the overall overall reaction. Okay, so adding the reactants, adding all the products, okay, then we will have and then the overall reaction is going to be 2 of the N2O Did you guys get this? Okay. For the rate law, it's going to be determined by the slow reaction. So we know that rate law is going to be constant K multiplied by concentration of the reactant in the first step or the slow step, which is nitrous oxide. Okay. So now that we have took a look at the mechanism with the slow initial step, here, slow initial step. So far, we have looked at the reaction with slow initial step. We're going to take a look at the equation with a fast initial step. Okay, so according to this rate law, let's take a look at the example where nitrogen monoxide plus bromine equals the NOBr. Okay, and this reaction, the rate law is found experimentally. According to this rate law, one possibility is that the reaction occurs in a single thermomolecular step. Okay? We can propose this according to this rate law. We can propose this thermomolecular reaction according to this rate law. However, as I mentioned before, thermomolecular process is rare, so this is unlikely to occur. So then we need to propose a different mechanism where it doesn't involve thermomolecular reactions. Okay. So this is unlikely. So what we proposed is not good. So we want to propose a better reaction mechanism. So again, same as before, overall reaction is given, overall rate law is given, okay? And we are already providing information that initial step or step one of initial step is faster, okay? With the three provided information, experimentally found and provided information, we want to propose a step one and step two mechanism. Okay, that's what we're doing. So now let's consider an alternative mechanism that does not involve thermomolecular step. Then we can propose multi-step equation like so. Okay. And note the reversible sign here. Step one involves forward reaction and reverse reaction as well. And this specific reaction is it's experimentally found to be reversible. Okay, it's just like hydrogen plus oxygen becomes water. We just know that nitrogen oxide plus bromine equals to this product, and this reaction is experimentally found to be reversible. Okay. Since we already provided the information that step two is a slow step, this is going to be the rate determining step. And we know that the rate of overall reaction is governed by this slow step two. So if we write the rate law in terms of step two, we can write this. K2 because it's reaction from the reaction constant from step two of the reaction. So I'm going to use label K2. Okay. This is the rate law using step two. Okay. However, note that NOBr2 is an intermediate generated in step one. Okay, and intermediates are usually unstable and it has low and unknown concentration. It is not ideal to write a rate law in terms of an intermediate. Okay, so we don't want to it is not ideal. We don't want to write the rate law in terms of intermediate. Okay, so let's find a way to substitute this intermediate with some other expression. Okay, so in order to substitute this intermediate NOBr2 with some other expression, let's take a look at the reactions that NOBr2 can take place. This compound can participate in two different reactions. For step one, it can decompose to generate nitrogen oxide and Br2. Remember, this reaction was reversible. NOBr2 can participate in this decomposition reaction. Step 2, NOBr2 will react with nitrogen oxide to form NOBr. Okay. For step 1, since this is a reversible reaction, when it's a reversible reaction, we know that the rate of the for reaction equals the rate of the reverse reaction. Then the for reaction for step 1, here, the for reaction for step 1 would be K1, rate constant for step 1, the for reaction rate law is going to be this. The reverse reaction rate law is going to be K, I'm going to label as -1. Reverse reaction of step 1, okay, is going to be NOBr2. Okay, because when the reaction is reversible, these two rates equal to each other, we can write this expression where for reaction equals the reverse reaction. This is plug in here, this is plug in here. Okay, this is the rate of the for reaction equals rate of the reverse reaction. If we solve for this, we can write this expression. NOBr2. If we solve for this, we have K1 NOBr2 divided by reverse reaction rate constant. If we plug this into, if you already forgot the original rate law that they provided, the rate law, overall rate law that they provided was this. It's already here. This is the rate law that provided. And then what we've been solving is we've been solving for this. Okay. This was the rate law from step 2, the slow reaction. However, we don't want to express the rate law in terms of the intermediate, so we were on a journey to find a different expression to substitute this intermediate. Now that we have different expression for this intermediate, we can substitute this into here, this entire part. Oops. This entire part is the NOBr2, okay? And because rate of the for reaction, yeah,
Wait,
go ahead.
can you just pause while I write this down? You're going really fast.
Oh, okay.
And I'm like so confused. Thank you.
Yeah, So again, we have this rate law from the slow reaction, step 2 reaction, but then we don't want to express the rate law in terms of an intermediate. So we were on a journey to find a different expression for this intermediate, and we have successfully found a different expression for this intermediate, which is this. We're going to substitute NOBr2 with this that we just found. So K2 is still K2. NO is still NO. This NOBr is this. Okay. And because forward reaction equals the reverse reaction, the rate constant for forward reaction equals the rate constant for reverse reaction. If they're equal, this will be 1, right? So then the overall rate is going to be, you are left with K2 NO BR2. This is the overall rate law that they provided from the experiment. Okay. So we have proven that the proposed step 1 and step 2 mechanisms meets the overall experimentally found rate law. So what we proposed makes sense. Okay. And in general, when a fast step is the first step, when slow step is the rate determining step is the following step, we can solve for the concentration of an intermediate by assuming that the equilibrium is established in the fast first step. Okay, let's take a look at, let's do a practice problem. You'll have a better idea.
Is there any way you could record what you're about to do right now? Because a lot of us are having a hard time keeping up. Like,
Record?
Yeah, if you could like start recording the lecture right now. Because we're in a group chat and we're all talking about how it's very hard for us to keep up right now. Taking notes and listening.
Oh, okay. I can't record. I cannot record. So I'll try to go as slow as possible. Okay. So do you want me to go back to this slide?
If you could just explain it one more time.
Okay. So where do you want me to start?
From the beginning.
Okay. So I'm going to explain one more time. We are provided overall equation. Okay, this is the overall equation that they provided. We're provided with this information. And then from the experiment, we know they provided that the overall rate law looks like this. They already provide the information that initial step is faster. Okay, so we have fast initial step. We are provided with 3 information, and we have to propose a step 1, step 2 mechanism. We need to propose a plausible mechanism that agrees with all the information provided from the experiment. So do you know the purpose of what we're doing right now? Okay.
Yeah.
Yeah. All right. So
Actually,
yeah.
What is the purpose? Why are we doing all this? Are we like trying to determine the rate law? Is that why we're doing all this?
We already have the rate law. We already have
Okay.
the rate law here, right? But then
Yes.
we want to propose a plausible mechanism. So we know that these are multi-step mechanisms, right? So we want to propose a
And these propositions, we create these propositions? Or are these propositions, are they going to be given to us?
So in your exam, you're going to be given your same type of question will be given. You will be provided overall equation. You're going to be provided with the rate law, overall rate law, and you're going to provide information whether first step is fast or second step is fast. And you need to be able to propose a multi-step mechanism. You need to come up with step 1 mechanism and step 2 mechanism. Does that make sense?
Yes, no, I understand that. And then for the term molecular, which is a rare instance, you provide 3 steps, right?
Yeah. So if you see rate law something like this, you immediately think, oh, it could be term molecular, right? But because like I mentioned before, term molecular in the real life is very, very rare and unlikely to occur. It is not likely that this reaction is a term molecular reaction. So when you see an expression with term molecular, no, we're not going to consider it as a term molecular. We want to find an alternative multi-step mechanism. Does that make sense?
Yes, I think the hiccup that the students are we're trying. I'm not sure. I'm only speaking for myself, but
Yeah.
maybe we're having problems to create these propositions for the steps.
Yeah. Okay. So
Okay.
just know the purpose. Just know what where we're going for. We're going for proposing a multi-step mechanism for this overall reaction. Did that clarify a little bit? We want to
Yes.
propose a multi-step mechanism. Okay, so we want to come up with the step 1. We want to come up with the step 2 mechanism that agrees with the overall equation. We are only provided overall equation, but we don't know step 1 and step 2 reaction mechanism. So we want to find out step 1 and step 2 mechanism. That's what we're doing. Is that clear?
Yes.
Okay. All right, so we are provided with this rate law, but then term molecular reaction doesn't really make sense in real life. So we are going to propose an alternative mechanisms, which is a multi-step mechanism. Okay. So if we want to achieve this overall equation, okay, this is what I can propose. There can be different variety of reaction mechanism combination that can agree with this overall equation. This is one propose. I'm proposing an equation that can agree with this. Okay, I'm proposing an equation. If this does not meet all the criterion for the plausible mechanism, I cannot use these equations to explain this overall equation. Okay, so this is what I'm proposing. Let's see if what I proposed agrees with these. Let's see if what I proposed, the mechanism that I proposed, agrees with these experimentally found information. Is that clear, everybody?
Dr. Lee.
Yeah.
So are we pretty much trying to prove the validity for the equation of the reaction? Is that why we're proposing these steps?
Yes.
Okay, I get it now. Thank you.
Okay. Yeah. So yeah. So we proposed two mechanisms and we want to check the validity, or we want to make sure, we want to check and prove, see if these mechanisms that we proposed agrees with the experimentally provided information or not. Okay? So then if you know the purpose, if you know the purpose, the rest is all math. So it looks confusing to you because these are all divided into different slides. What I recommend you guys to do is after the lecture, try to summarize all these math into one piece of paper. The math is very, very simple. Okay, so the exercise that we're about to do is going to be very similar to what I've just done. So I'm going to show you how to I'm going to show you all of these in a single piece of paper so it's easier for you to follow. Okay, so does anyone else has question about what we're doing, the purpose of all of these? Does anyone want me to explain one more time? Okay, so I guess we're clear on the purpose part. Okay. So let's take a look at the equations. Let's say this is another equation that we proposed. Step 1 and step 2. These equations are different from these that I proposed above. Let me copy and paste this. Are they same or are they different? They are totally different. Step 1 mechanism, step 2 mechanism, they're different. This is what I proposed earlier, and this is what other people proposed. Okay? We want to check and see if they said that the rate law they say these mechanisms and these mechanisms will agree with both will agree to this rate law. We're going to see if that's actually true or not. Okay, so what I'm trying to say is when a rate law is given, you of multiple different variety of mechanisms can agree to the experimentally found rate law. You can propose various different mechanisms. They just have to agree with the rate law. Okay, so this is not the definite answer for this rate law. You can have this mechanism, and some other mechanisms that agree with this rate law. Okay, so again, this is what I proposed, and now what we want to prove is whether these mechanisms will have this rate law or not. Okay, so that's what we're going to do. Okay, so Since the second step is a slow step, we know that the rate for this reaction, according to this mechanism, is going to be like so. Okay. Does anybody have questions up to this part? Okay. And step 1, the fast step, we know that for reaction equals the reverse reaction. From the fast step 1, we know that the rate of the for reaction equals the rate of the reverse reaction. We can also write Does everybody agree with this? This is the rate of the for reaction, and this is the rate of the reverse reaction. K1 is the rate constant for reaction for step 1. K negative 1 is the reaction constant for the reverse reaction for step 1. Okay? So then if you go back to the rate equation, we have N2O2. And from here, it looks like N2O2 is an intermediate. And as I mentioned before, we don't want to express rate law in terms of intermediate. The reason is because intermediates are unstable, low in concentration. It's going to be made and quickly consumed during the reaction. So we don't really want to have intermediate in the overall rate law. So we want to find some other expression rather that can substitute the intermediate. Okay? So that's what we're doing. So we know the rate of the for reaction equals the rate of the reverse reaction. So rearrange this. You will have this. This is the intermediate. This is the intermediate. If this equals this, can you substitute this into here?
Quick question, Dr. Lee.
Yeah,
How do we identify intermediates?
intermediates, if you look at step 1 and step 2, the easy way to do is you write the overall equation. So you add all the reactants and you add all the products. If they can, if anything that you can cancel out, then that's typically intermediate.
Okay, yes, I remember you
Yeah.
did that a little bit ago.
Yeah.
Thank you.
Yeah. But yeah, or easier way, if you see it here, you know that, oh, it should be consumed. So yeah.
Similar to how we deal with spectators.
Spectators?
Well, like well, never mind.
Oh, okay.
Yeah.
Okay. So, yeah, I skipped the part how to identify intermediate, but in order to find intermediate, write the overall equation and then see if which one cancels on both sides. That's typically your intermediate, okay? But yeah, so N2O2 is going to be your intermediate. And now we have different expression for your intermediate. So can you substitute this into here? Okay, if you substitute that, you're going to have something like this. Mm. Oh, wait, just- Okay, because K1 equals K minus 1, the reason is because rate constant for forward reaction equals rate constant of reverse reaction. This entire thing is 1. Okay, so then you have a rate of K2 oops. You have finally achieved this rate law. Now let's compare with the rate law above. Are they same or different? They are same. Okay, what this tells us is that from this rate law, you can propose this mechanism that I propose, and this mechanism will meet this rate law. If you are given this rate law and if you propose this mechanism, it will also meet this experimentally found rate law. So with the single rate law, you can propose variety of different mechanisms, but you want to double check, you want to validify, you want to prove that the mechanisms that you propose is a plausible mechanism or not. So this is all you guys have to do. So is this better, or are you guys still confused?
That one was
Any
way.
Questions?
Sorry.
No, this explanation was easier to understand.
Yeah, okay.
Yeah.
So, yeah, so I really think the only reason that you guys were lost is because the math was divided into several different slides, but the math is actually very, very simple and easy. So what I recommend you to do is after this lecture, reorganize these 4 slides into one piece of paper. You will have much better idea. Okay. Again, there may be more than one mechanism that leads to an observed experimental rate law. Okay, there can be more than one mechanisms. This is the mechanism that I proposed. This is a mechanism that other people propose, but they all leads to the experimental rate law of this. Okay.
I have a question.
Mhm.
So would like the final answer just be yes, they agree, or like what would our answer be to the question?
So the question is asking us to show. So since we showed and we arrive at this rate equation, we say that this rate law, after solving this, we arrived at this rate law, which agrees with this law. So yeah, this mechanism agrees with the rate law. So the equation 14.26 is going to be this equation. Okay, so you can say that because after all these, you arrived at this rate law, and because this rate law agrees with this equation, the equation 14.26, you say that this mechanism also produces a rate law consistent with the experimentally observed one. Okay, so the whole purpose is showing the entire process. And you say that yes, they agree with the equation 1426 rate law of this.
Dr. Lee,
Yeah,
in the rate law, for step 1, does case subscript 1 and case subscript -1 have the same value but different sign?
different sign. They need to have different sign because
But same value, right? Numerical value, or
yeah, they should have same value because we know that we assume the rate of the forward reaction equals the rate of the reverse reaction. But rate constant, so it's just like F and R. They're same, but we want to label it differently, right? So same thing for rate constant. They're different. Their values are same, but we want to label them differently because they're technically not the same thing. You know what I mean?
so then so that's why case subscript 1 divided by case subscript -1 gave you 1?
Yeah, one. They're same.
It wouldn't be a -1?
No, this is just a label. It's like A, B, C, D.
Got it.
Yeah,
Got it.
not
Thank
not
you.
not number one.
Okay.
Yeah. Okay. If you guys are still confused after reorganizing the lecture note, you can always schedule an office hour with me. Okay. All right. In the previous slides, we have just learned about plausible reaction mechanism. Okay. The plausible, they say plausible reaction mechanism would have stoichiometry obtained when all steps are added up. Each step needs to be balanced. All intermediates are made up and used up. Any catalyst is used and should be used and regenerated after the reaction. We never dealt with any catalyst before because we didn't see any examples utilizing catalysts, right? So from here now on, we're going to focus about catalyst. Okay, so what is a catalyst? Catalyst decrease or lowers the overall activation energy of a reaction. Since the energy barrier is lowered, lowered, the overall reaction rate is increased. Okay, catalysts, take a note, catalysts are not consumed in the reaction. Okay, catalysts are not consumed in the reaction, you will regain or regenerate catalyst in its original form at the end of the reaction. Regain or regenerate after the reaction. Okay. Catalyst is just a helper. It's boosting the reaction speed. It's only helping the reaction to occur faster. Okay. So you might ask, will the reaction still happen without a catalyst? Yes. A reaction without a catalyst will still work without a catalyst, but if you have a catalyst, it will happen faster. So it's like a booster. There are three types of catalysts: homogeneous catalysts, heterogeneous catalysts, and enzymes. Okay. First of all, let's take a look at the homogeneous catalyst. For homogeneous catalysts, the reactants and catalysts are in the same phase. They're in the same phase. Okay. For example, look at the diagram here. Your reactant hydrogen peroxide is in solution form. Okay. Although sodium bromide is solid, once you add into the reaction mixture, it becomes homogeneous with the solution. It dissolves in the reactant. Okay, then because the solid form is now completely dissolved in the reactant and present in the same phase as the reactant, you see clear solution here. We call this catalyst homogeneous catalyst. Okay. When the reactants and catalysts are in the same phase, we call this catalyst homogeneous catalyst. Let's take a look at example of the heterogeneous catalyst. Okay, heterogeneous catalysts are in different phase than reactants. For example, solid catalyst in contact with, this is a solid catalyst in contact with hydrogen and carbon. These are the gas state reactants. If solid catalysts react with gas, okay, they are in different states. We call this heterogeneous catalyst. Okay, absorption of the reaction reactant is often the rate determining step, which means binding of these reactant molecules to the surface of the catalyst will govern how fast or slow the reaction can occur. So if solid catalyst is in a finely powdered form instead of solidified clump, more reactants will be able to react on this surface and faster reactions can occur. Just 2 more slides. So while there are countless chemical catalysts that occur naturally and man-made catalysts in the lab, there are also biological catalysts. Okay? Enzymes are biological catalysts that are crucial in our human body. For example, hydrogen peroxide. Hydrogen peroxide is very harmful to our body. So the blood and liver of mammals contain enzymes called catalase. Okay? This is an example of an enzyme in our human or mammal's body. This catalase will catalyze the decomposition of hydrogen peroxide into water and oxygen. Hydrogen peroxide into water and oxygen. The diagram is showing the grounded beef liver added to a beaker with hydrogen peroxide, immediately reacting to form water and oxygen. And because the beef liver contains enzyme called catalase, this reaction is occurring faster. Okay, and since hydrogen peroxide is very harmful, very harmful to our body, we want to decompose. We want this decomposition reaction to occur very fast, and catalase is speeding up that reaction for us. Okay, last slide. For biological catalysts, the enzymes, the reaction doesn't occur everywhere. The reaction of enzymes takes place at a specific location called active site. Okay, the substances that react at this active sites of an enzyme. So these are the active site of enzyme. And any substance that react with the active side at an active side of an enzyme is called substrate. These are the reactants. Okay, these substrates are reactants. The specific substrate will fit into a specific active site of an enzyme, just like a key fits into a lock. And this is called the enzyme substrate model. Okay, and that is it for chapter 14. I'm going to upload this PDF file with the notes on it on Web Campus by tonight. Okay, so yeah, please reorganize this section into a single piece of paper. If you have further questions, schedule an office hour with me. I'm going to stay for another 5 to 10 minutes just in case anybody else has questions.
I don't have a question, but I did want to apologize for coming in late. I had a doctor's appointment. Sorry.
Okay.
Thank you, Dr. Lee. See you Thursday.
Okay, see you. If you don't have any question, you can feel free to leave and I'll see you guys on Thursday, okay? I'm going to stay for another 5 to 10 minutes.
I have a question for the exam.
Yeah.
Are we gonna have like how would we be asked to show that it all agrees with the rate law or show
Yeah.
that?
So there are a few things that you need to memorize on top of your head, such as rate of the forward reaction will rate of the reverse reaction, and using that information, you can rewrite the intermediate in different expression. Okay, so these kind of things you want to do a lot of practice. So I would solve these kind of problems multiple times and try to get used to how to re-express the intermediate in different form, because you definitely don't want the intermediates in the rate law expression. Okay, so those things you want to be comfortable with.
Okay, thank you.
Mm-hmm.
Question 5, not like the wave equation. I think it comes to 9 to pass on